Okay. Um, so let me start by just sort of talking generally about statics, what kind of stuff we're going to cover, and then we'll get into the vector review, just vector calculations. I know you've seen all these things before, but I'll sort of emphasize the ones that are going to be important in this class. So this statics is part of a general area of engineering calculations called mechanics. And I would say it kind of goes like this, is in a tree structure. So statics is sort of the beginning of all of it. And from there, it kind of branches into deform on one side and dynamics on the other side. This side has to do with kind of calculating are we in danger of having this structure or material break? And if so, where is it going to break? Dynamics is more, you can think of this as like, how will it move? And then from deform, you can separate this into two areas. One is a very mathematical area called continuum mechanics that doesn't end up, for the most part, being that applicable to, like, it's more and more, it's just kind of an area of math departments, you know, but continuum mechanics. Instead, like when companies need to do deform type calculations, they tend to use finite elements, which is a numerical approach to doing complicated deform type calculations. Finite element analysis. So it's just a numerical approach. If you ever see something like all capitals FEA or FEM, that's finite element analysis or finite element method. That's what they're talking about. And you can use this for really complicated shapes. Even the best mathematicians, there's just no way to approach very complicated geometry or really complicated loads. You're just sort of limited if you're doing hand calculations. And in a way, you know, for the people who are going to take deform, I mean, I assume the majority of people who have to take statics at some point have to take deform too. I call it deform because that's what they call it at the U, and most of our students go to the U, but other universities usually call it mechanics of materials. But I would say, practically speaking, the main reason you need deform is to understand the results that you get from finite elements. Like when you're working in a company, you just need to understand these ideas in order to interpret what you're getting out of the computer, and to do sort of sanity checks, like to get an idea of like, okay, those stresses should be somewhere in the ballpark of this. Then you run the computer and you can tell whether you likely have a big mistake somewhere or not. Okay, so, and then on the dynamic side, you start out with the, so you start out with force approaches. Anyone remember what's, so I said force approaches and energy approaches. Each one's named after a famous mathematician. Anyone remember what force approach? Lagrangian, yeah. So, sorry, I have that backwards. I had that backwards before. So don't listen to what I said before. Eulerian. And then from there, you can go kind of in two directions. You can go to Lagrangian. So this is the force approach. Lagrangian dynamics is the energy approach. And the other branch here goes off from, if this is all solid dynamics, the other branch is fluid dynamics. Okay, so that's kind of a rough layout of how these classes would go after you take statics, but statics is kind of the beginning of all of this big topic. So in statics, we're going to be talking about a force-based approach using Newton's laws. And if you have static equilibrium, well, generally speaking, if you have a dynamic problem, Newton's second law tells you that the sum of all the forces is equal to the mass of the object times its acceleration. And you can use that law to derive the rotational equation that says the sum of all the moments about some point is equal to the moment of inertia about that point times the angular acceleration. In static equilibrium, you don't have any acceleration of any points, and you don't have any angular acceleration, and so this reduces to the sum of all the forces is equal to the zero vector, and the sum of all the moments about any point is equal to the zero vector. By the way, I think most of the time when you take physics 1, you don't have a lot of time to go into details about this rotational equation, but this only applies for at most 2 choices of the point A. So that's a pretty stringent requirement on what you're using as your about point for calculating moments and stuff. Here, static, it works for any point A. So these are going to be the 2 main equations that we use. If we're doing 2D problems, force is a 2-dimensional vector, so we have 2 equations from the force from Newton's second law. And if you're in 2 dimensions, you're in the plane, so all rotations are happening about an axis perpendicular to the plane. And so this equation gives you only 1 extra equation. So in 2D, you have 3 total equations. In 3D, you have 3 and 3, so you have 6 total equations. We'll talk about all that more. But so either 3 equations, more commonly, we'll be doing a lot of 2D problems, or 6 equations if you're doing full 3D. What's required for those to hold? To be able to use those equations, for Newton's second law to hold. you need to have an inertial coordinate system, okay? If you don't have an inertial coordinate system and you measure all these things, it's going to look like those equations don't work. So here's an example, sort of a thought experiment. So imagine that you have, okay, so imagine you have two scooters. Okay, so there's a scooter, and it's connected rigidly to another scooter. And let's say that this scooter has a video camera mounted to it. And that video camera, so this is the coordinate system. Okay, you can think of, anytime you're thinking about a coordinate system, you can think about a video camera that's monitoring the action. Okay, and that video camera is telling you from wherever that video camera is, how far in this direction, how far in this direction, where everything is. Okay, that video camera is monitoring the location of objects that it sees. And let's say here you have someone on this other scooter. Okay. So what does it mean for a coordinate system to be inertial? What are the requirements? Did that come up in Physics 1 at all? Inertial and non-inertial coordinate systems. So for an inertial coordinate system is one where the origin of the coordinate system is moving with a constant velocity. So the origin isn't accelerating. I guess let me write this down. Origin doesn't accelerate. And second, the axes don't rotate. Okay, so if these are moving with a constant velocity, so say these are moving just straight to the left, straight to the right with a constant speed, and they're not changing directions, then this camera represents an inertial coordinate system. And in that coordinate system, if you measured the forces being applied to this person, okay, that camera, so if this person riding the scooter is just standing there like this on the scooter, okay, and the whole system is moving to the right at a constant speed, okay, what is the acceleration according to that camera? So imagine looking at the video of that camera. What's that camera going to see? It's just going to see a person standing in front of it like this, right? So it's going to say that person doesn't have any acceleration or any angular acceleration. That person's just still, okay? So in that inertial coordinate system, Newton's second law says there should be no net forces on this person. So add up all the forces on this person, it should add up to 0. Okay? That's what statics says. That wouldn't work, on the other hand, if this is accelerating. Okay? So imagine so now imagine that this person's standing here and somebody, some strong, a cable's attached to this and it's attached to a truck, and the truck takes off and accelerates this whole system to the right. Okay, so now there's acceleration. This camera now is going to measure an acceleration of this person, what's it going to look like to the camera that that person does? I mean, so yeah, I guess it depends how strong he's holding on. If he's not holding on very strongly, it's going to look like he accelerates backwards, right, off the scooter. If he's holding on strongly, it's going to look like there's zero acceleration on him, right? So if you think about that, he's still holding on, but the force sensors here and here are all of a sudden going to measure these high forces, right? And if you added it up, it would look like when you combine the force information with the acceleration information from the camera, it would look like Newton's second law didn't hold. Okay. So anyways, that took a long time, but the basic idea there is this stuff does not work if your coordinate system is non-inertial. It only works if the origin is non-accelerating and the axes are not rotating. This is required for Newton's laws to hold. And the kind of calculations, so the types of problems that we're going to use Newton's laws for, the types of problems we're going to do in this class. One example is, this is something we're going to do a lot of. You can imagine a structure made up of several different members. So say that these are connected by pin joints here, here, and here. And say that you have an object being held by these clamps. And you know that some amount of force is being used to press down on the ends of these, they're not really pliers, but this structure. And you want to be able to calculate what is the net force, or I guess what are the forces applied to the top and bottom of the object. Okay, that's the kind of calculation that we're going to do a ton of times in this class. So based on the geometry of this, we'll be able to calculate all the forces happening at these different joints, which you could use to figure out how likely it is that this pin is going to break or that this object is going to fracture or whatever. Okay. And you can use it for, obviously this is engineering materials. It's probably made out of steel or something. But you can also use it for problems where you're not dealing with engineering materials. Like for example, say you have a diver. Okay, so this diver's standing here on the platform ready to dive. You could treat that as You know, it depends what parts you're focusing on. If we don't care about the upper body, we can treat that all as one thing and just treat it as if it was engineering materials connected by joints. And external forces are applied by muscles, like say, here's a gastrocnemius muscle going from the heel to the thigh. And you could calculate, to stand in this position, what's the tension in the calf muscle that's shown there. Or you could calculate what's the compression at the knee joint or at the ankle joint. And these are the kind of things you would use a calculation like we're going to do in statics to figure out what's the likelihood of injury, or if there's any way you can optimize this position to, you know, put a smaller requirement on the bone or on the muscle or whatever. Okay, so these are the kind of calculations that we'll be dealing with in statics. Anyone have any questions about sort of the overall idea of statics? We're going to be using Newton's second law, and we're going to be mainly figuring out the forces at different points inside of structures connected by joints. All right. Well, let's go into a review of vector calculations. On D2L, there's a PDF posted on there in the content section. Has everybody here used D2L before for a class? You know how to get into your D2L? That's going to be really important in this class. So if you have any trouble getting in, let me know. And we need to, you need to figure out how to get into D2L soon. You should probably get in the habit of checking it every day for new stuff. But in the content section, one of the things that I put in there is a little document vector review that goes over the kind of calculations we're going to do. And at the end, there are 12 or so problems. And you should be able to do those problems and problems like them. And that material is going to be covered on the test. Okay, so you should start working through that vector review. I think for a lot of people in here, it won't be very hard. You could, without even reading the document, you might be able to work through the problems on your own. But if you have any trouble with the questions, you need to read that document and get ready to answer questions like that. But I'll go through some of it right now. So there's a PDF posted in D2L. So you can think of a vector is a mathematical object with a length and a direction. And so it's easy to, it's sort of natural to represent it as an arrow. Where the length of the arrow gives its magnitude and the direction, is shown by where the arrowhead is pointing. Like, for example, this is a vector. It has a length of, in this case, let's say 1.5, and let's say that this angle is 30 degrees. Okay. So that's the vector. the components that represent a vector, that's not a vector. That's a mathematical description of it. What do you have to define in order to go from this actual vector to representing it in components? A coordinate system, right. The components are dependent on a coordinate system. So to represent this as vector components, you must specify a coordinate system. I'm going to just always abbreviate that CS. I'm going to use that all the time. In 2D, once you specify a coordinate system, you can represent a vector like this. And this is the notation I'm going to use, square brackets with the first component on top and the second component on the bottom. Okay. And in 3D, you'd have 3 components. And keep in mind that a 2D vector like that also lives in 3-dimensional space. And so this is really shorthand for x, y, 0. Okay. To multiply a vector by a scalar, so say that your scalar is c and you're multiplying c times this vector x, y, z. That just gives you cx, cy, cz. To do that in a TI-89 calculator, you could do a problem like this as 5 times, so c would be 5 here, and the vector would be, as an example, 1, 5, -8. And this would give you the value, the output 5, 25, -40. So in a TI calculator, this is how you represent a vector. On some of the older versions of TI calculators, you have to go into the matrix area to do these calculations. Let me know if you want help figuring out how to do that. But to add 2 vectors, if you have a vector AX, AX, AY, AZ, and you're adding it to a vector BX, BY, BZ, that gives you a new vector AX plus BX as the first component, AY plus BY as the second component, and AZ plus BZ as the third component. In a TI-89 calculator, you could do that as 1, 2, 3 plus negative 1, negative 1, 1. The semicolons here in this notation mean that that you're changing rows. So this is making it a column vector. If you did commas instead, it would be a row vector. Okay, we're treating our vectors as column vectors. And so this would give you 0, 1, 4. So it's just adding the first two components, adding the second two components, adding the third two components. To calculate the length of a vector, calculate the magnitude of a vector. Okay, so if your vector v has components vx, vy, vz, you can represent the magnitude of v like this, use an absolute value symbol. How would you calculate the magnitude from that? Yep. That's right, and it's just the Pythagorean theorem. You're trying to come up with a three-dimensional hypotenuse where those are the perpendicular, components. So you do it as Vx squared plus Vy squared plus Vz squared, all square root. And the TI-89 has a built-in function for this called norm. So you just do norm of, let's say we have one that's 3, negative 4, these should be semicolons, 0, in this case, this would be a 3, 4, 5 triangle. So the length of this vector should be 5. And so if you do norm of this vector, it would give you the value 5. Another calculation that we're going to use a lot is unit vector. Calculate the unit vector that's in the direction of a given vector. So let me first just give a little description of why this is going to be useful. Any vector, so the definition of a vector is something that has a magnitude and a direction, okay? You can break vectors up always into a number that represents its magnitude times a unit vector that represents its direction. So the length, the magnitude of the vector, the magnitude of the vector represents its length, and the unit vector represents its direction. So we're just always going to break vectors into a scalar magnitude times a vector that represents direction. This one is the length, and this one is the unit vector. Okay, so if, again, you have a vector v that's defined as these components, how do you calculate a unit vector in that same direction?
Each one divided by magnitude.
Yeah, that's exactly right. So basically, so you can think of, if every vector is its magnitude times its unit vector, then dividing that vector by its magnitude has to give the unit vector. Okay, so this is going to be, so if this is v, then a unit vector in the direction of v that you represent with a caret or a hat is equal to 1 over the magnitude times the components. Okay, so if you want to calculate a unit vector in the direction of this, first calculate the magnitude the way we did here, and then just divide every component. In a TI calculator, there's a function that does that. It's called unit V with a capital V. And so, like, if you type in unit vector in the direction of 1, -1, -1, that'll give you the answer. So, well, the magnitude of this is going to be the square root of 3. And you divide each of these by the square root of 3, and you'd get a vector out that is 0.577, -0.577, -0.577. Why are unit vectors common in statics? Well, there are a lot of cases, including forces applied by cables or forces applied by certain kinds of joints, where we don't know the magnitude of a force that's being applied, but we do know the direction. So cables and certain joints apply force vectors with unknown magnitudes. You know, that means we have to calculate the magnitude. but known directions. So for example, say that we had this big beam connected to the wall by a pin joint. And over on this side, it's connected to another wall by a cable. If we draw a free body diagram of this beam, we'll talk about the forces applied by joints later, but for now, I'll just tell you this is going to be an unknown force vector. We don't know anything about either component. Okay. What do we know about the components here? Well, we don't know either component, right? We don't know the x component of this force. So now let's say there's a cable tension T applied in this direction, right? To represent this as a force vector, we don't know either component. But we do know that the force vector applied by the cable is T times U where U is the unit vector in the given direction. Okay. Well, then if we're trying to figure out what the cable tension is here, you know, at first thought, you might think, well, this is a force vector and we don't know either component. So we have to represent this as two unknowns, right? An x component and a y component, right? If you don't know either component, then you got to solve for both of them, right? But if instead you represent that force vector as a scalar value times a unit vector that you can come up with numbers for, you can see that the vector is actually, you can represent it as, you know, T, you know, depending on, let's see, if this angle, say, was 45 degrees, that unit vector is just going to come from cosine and sine. Then that force vector is just going to be T times, or, you know, 0.7071 T, 0.7071 T. And now instead of having two unknowns, we've represented this force vector with a single unknown. Okay, that's the benefit of this. And since you're always trying to come up with, I mean, in any kind of engineering calculation, you're trying to come up with enough equations to solve for all your unknowns. If you can come up with a way to reduce the number of unknowns, that means you have fewer equations you need to come up with to solve it. And usually that something like this will be the difference between there being a solution and having no way, you know, having a solution not occurring. Anybody know what I'm talking about? Good. Okay. Well, we'll go into more detail later, but this is the kind of problem where unit vectors are really useful in statics, and so we'll use them all the time. It's a way to take a vector and treat it as a separate magnitude times a separate direction. And the unit vector is the direction. It lets you reduce the number of variables. Okay, so next is multiplying two vectors together. So remember, with adding, there's only one way to add two vectors. You just add the components. Multiplying, there's multiple ways to do it. There are really only two that are going to be useful to us. One's the dot product and one's the cross product. And they both are useful for different reasons. The first one, dot product. It's often called the scalar product. And the dot product between two vectors, if you have ax, ay, and az, and you're taking the dot product with bx, by, bz, it gives you the value ax bx plus ay by plus az bz. So why is it called the scalar product? Because the output is you take two vectors and put them in, and the number you get out is just a number. It's a scalar. Okay. On a TI-89, there's a function that does this. So dot p with a uppercase P of two vectors, let's say 1, 1, 2. Whoops. Yep. So for inputs, you have to provide two vectors separated by a comma. And so the second one, let's say 0, 0, 1. And that would spit out the answer 1 times 0 plus 1 times 0 plus 2 times 1. So you get an answer of 2. There are two things that you need to keep in mind about the dot product. So notice two things about the dot product. The first one is this is really kind of three things, but they're pretty related. Two perpendicular vectors, what's their dot product? 0, yep. Two vectors in the same direction. How did I word this? Okay. Sorry. Just take your electric pencil and just erase it, and it'll be like it was never there. So the maximum positive value for a dot product occurs when the two vectors are in the same direction and the minimum, the maximum absolute value, negative value occurs when the vectors are in opposite directions. And then the second thing I want you to keep in mind is that the order for dot product doesn't matter. So if I switch the order of these two, you'd get the same thing for the dot product. The order of the input vectors doesn't matter. The second type of vector multiplication is the cross product. This is sometimes called the vector product. If you have AX, AY, AZ crossed with BX, BY, BZ, you get AYBZ minus AZBY. It's sort of this ridiculous looking formula. AXBZ minus AZ, what did I do? This should have been BZ. And then the third component is AXBY minus AYBX. And you can see this is called the vector product because you input two vectors just like you do for the dot product. But the dot product, you get a number as an output, and this you get a vector as an output. On a TI-89, there's a function for this called cross P. Can anyone look at this and tell me what the value is of this cross product? Yep, it's 0 because that's one of the things that I want you to keep in mind about cross product. Wait, it's not 0. That would be dot product. Sorry, that's wrong. It would be, so let's see, I have to think about it. That would be y, right? So this would give 0, 1, 0. Because of this. So these are the things I want you to notice about the cross product. First, the output vector is perpendicular to both input vectors. Now, how many vectors are there that are perpendicular 2. So say you have 2 random vectors. Here one's going this way and one's going this way. How many vectors are perpendicular to both of those? Well, and don't, without considering magnitude. So how many directions are perpendicular to these two? 2. One this way and one the opposite way. Okay. And you choose which one of those 2 is the correct direction by the right-hand rule. So it's perpendicular to both input vectors according to the right-hand rule. And then this is the last thing for today. The second thing you need to remember about the cross product is order matters in this case. Switching the order switches the sign of the output vector. Anybody have any questions about any of this? Okay, well, I would recommend, start looking through that vector review, see if you can do those questions. I'll open up whatever lab is free. And yeah, see you either there or tomorrow.